So now we're going to go into talking about a redox reaction and a bit of an overview into understanding these oxidation states a little bit better with the application of the oxidation and reduction, or our redox reactions. So basically, now that you understand the oxidation states, we can then apply these and cover our processes of oxidation and reduction. So there's quite a useful acronym which people use and you can use to remember these processes, so the processes of oxidation and reduction. And this acronym is called OIL-RIG. And so we say that oxidation is loss, reduction is gain. So oxidation being the loss of electrons and reduction being the gain of electrons. It's also good to remember that they sort of sound the opposite of the way they're meant to be. Because if you think about it, reduction seems like it should be a loss of electrons, but reduction is actually a gain of electrons. And you would think that oxidation is then going to be the gain of electrons, but it's actually the loss of electrons. And so this is basically these values, as I already mentioned, are referencing to the change of electrons which occur in a redox reaction. So basically, if a species is oxidized, it loses electrons, whilst if it is reduced, it's going to gain electrons. And then opposite to this is a change of oxidation states. So if a species is oxidized, its oxidation number is going to increase. So for example, you have something with a 2+ oxidation number and it becomes oxidized, it's lost electrons. If it's lost 1 electron, it will then become 3+, and that's because we remember that electrons have a negative charge. So if you're to take away an electron, that means you're taking away negative charge, giving the element a more positive charge. And so the species that is oxidized is called the reducing agent because it causes the other one to be reduced, whilst the species that is reduced is called the oxidizing agent because it's causing the other one to be oxidized. And the way in which it's causing the other one to either be oxidized or reduced by doing the opposite is because this is a sharing of electrons type process. So when the species is oxidized, it's losing electrons, but it doesn't just lose these electrons to nowhere because you can't create or destroy the electrons. So it's losing these electrons by transferring them to the species which is being reduced, hence it being called the reducing agent, because it loses its electrons and donates them to the molecule which is going to then gain the electrons. And so the species that is then reduced, so the one gaining electrons, is essentially taking electrons from the one which is being oxidized, hence causing the one which is being oxidized to then be oxidized. So these reactions are dependent on each other. You can't have an oxidation without a reduction, and you can't have a reduction without an oxidation. They work hand in hand because you need one in order for the other to occur. As I previously said, like you can't lose electrons to nowhere. They have to be given to another species. Same with, you can't just gain electrons from anywhere. They have to actually be taken from somewhere else. So it's important to note that these, as I said before, these redox reactions are composed of two parts. so the reduced half and the oxidized half. So you can actually split, instead of writing it as one big reaction, you can actually split these reactions into the reduced half and the oxidized half. So there's no net change in the number of electrons in a redox reaction, which means that no electrons are gained from or lost to the environment. So basically, as I said before, like in the entire reaction, there's actually not a net change in electrons. There's just a transference of electrons from one species to the other. So we can look at an example, and this example here uses zinc and hydrogen ions, and it shows us a transference of electrons, and it's also balanced to show how the ratios work such that you can have something with different charges create the same charge. So essentially, we want to look at what is happening here in this reaction. So if we're taking note of this, we can see that the oxidation state of the hydrogen is going from +1 to 0, because remember, applying our rules say that anything with a charge is going to, its oxidation number is going to be the charge of that given ion. And then our other rule states that anything that's entirely made up of one type of element is going to have an oxidation number of 0. Hence, hydrogen gas, or H2, has its oxidation state of 0, whilst H+, our hydrogen ions, has its oxidation state of +1. And so we can see it's changing from +1 to 0, and then our oxidation state of zinc is changing from 0 to +2. And so we can see this is going to be 0 because it's entirely made up of one type of element, and so hence that's rule 1, it's going to be 0. And then obviously with our zinc here, it's got a charge of 2+, and that comes to part of rule 2, in that the charge of an ion, if the entire molecule is an ion, then that's going to be its oxidation state, and so that's the rule here, where we've got zinc 2+, its oxidation state is going to be 2+. And so then we need to look at, well, what's being oxidized and what's being reduced. And so this is where it can get a bit tricky, in that you need to pay a lot of attention to the detail and remember that what is being reduced is gaining electrons, and what is being oxidized is losing electrons. And you then also need to consider that what is gaining electrons will end up with a more negative value than it started with, and what is losing electrons will end up with more of a positive value than it started with. So, for example, we're then looking at zinc, and we can say, well, zinc is going from 0 to 2+, so it's becoming more positive. We know electrons are negatively charged, so if zinc is becoming more positive, it must be losing electrons. And so when we say what is a reaction where the species loses electrons, that's going to be our oxidation reaction. So we can say the oxidation state of zinc is going from 0 to 2+, so it's losing 2 electrons and so it's being oxidized. And then we need to remember that what is being oxidized is going to act as a reducing agent. So we can say zinc is oxidized, and we can also say that zinc is the reducing agent. We can then look at hydrogen, and we can say that hydrogen is going from a 1+ charge to a charge of 0. So it's becoming more negative. It's going from 2+ with those 2 there, so 1+ per hydrogen, to 0. So where each hydrogen atom is going to be losing 1 electron. So when it's losing an electron, we remember that it's gaining 1 electron. It's going from +1 to 0. That's going to be a gain of 1 electron, because we're remembering that our electrons are negative. And so that means that it's being reduced. Hence, hydrogen is going to be reduced, and it's going to act as the oxidizing agent. So overall in this reaction, we've got zinc going from 0 to 2+, and it is being oxidized and hence acting as a reducing agent. And so it's giving away these 2 electrons and donating them to this hydrogen. So this hydrogen can be reduced and gain those 2 electrons, an electron per hydrogen atom, to then become H2 with its charge of 0. And so to look at this more clearly, we can also break it up into half reactions. So we can say that the zinc forms zinc 2+ plus 2 electrons, and you can do 2, and so that would be our half reaction for the oxidation of zinc, whilst we can also then do beneath that 2 electrons plus 2 hydrogen ions makes hydrogen gas, and that's showing our reduction reaction, which is showing the reduction of the hydrogen ions.